This is about the ensembling modeling. It's a second part. In the first part, we already seen what is a bagging. It is important part of ensembling modeling, and now we are going to the second part of ensembling modeling. It's a boosting. So basically, ensembling modeling is a combination of both bagging and boosting. So bagging we already covered with bagging, and we are trying to get the idea what is exactly boosting, and the practical how practically we can implement the boosting, that we are going to see in this video in this presentation. So I'll just take you through what are the topics which we are covering today. So it's an introduction of boosting. What introduction means, what we are going to cover today. Then what is the boosting? Then boosting, exactly what algorithm boosting algorithm is. Then different kinds of boosting algorithm. Then boosting case study with a small data set from UCI, and implementation of boosting in R. Then comparison of results between bagging as well in boosting. Means in terms of the scenarios, in terms of the usability, and in terms of the benefits between bagging and boosting, that we are summarizing at the end. Then the XGBoost, that is extreme gradient boosting. Exactly what is XGBoost, what is a gradient boosting, what is the extreme gradient boosting, that we are also going to see in the current presentation. And as well, we have the small case study of gradient boosting. It's a simple gradient boosting. It may not be the extreme gradient boosting, and the simple gradient boosting in R. And at the last, before going to Python programming, I just wanted to introduce what are the modules that we are referring from Python to handle this bagging as well as boosting, as well XGBoost, or you can say simply boosting. These are the topics which we are covering today. So just into the second slide. Fine. So what are the ensembles? I just covered the same terminology in the last presentation also, but I'm just refreshing it once again. The ensemble is a modeling, or it's a combination of the individual models. It can be simple, it can be complex. It is a combination of different individual models or the same individual models together to create a more powerful new model with a great classification accuracy, that is with a lower error. So our aim is to boost or to increase the classification accuracy, as well to at the same time to reduce the error rate. So that is the ensembling modeling, and within ensemble we are doing the combination of the same type of model, or we are trying the different model, and we are trying to combine all those models. So bagging already covered, as I say. So today we are going to see what is the boosting, and boosting is a second ensemble method, that is an ensemble model. This is a second ensemble model for improving the performance of classification as well as the performance of regression. So exactly what we are doing is, so boosting, what we are doing, we are trying to reduce the residual error, that is the error between predicted value and the error between predicted value and actual values. So once we are going through the case study, so we'll come to know what exactly we are doing in this. So basically in ensemble modeling, there are two parts. Either as in the last presentation we discussed, bagging plus boosting, and the same terminologies are bias plus variance. So exactly what happens in the algorithm, that depends on which method we are referring. Suppose we are considering boosting. So boosting may what happening? Boosting reduces our error of predicted values. So boosting works on weak learners. So what happens exactly in boosting? Suppose I fit the model for the case considered like decision tree or random forest, because in bagging we consider random forest. So consider random forest as a model. Then suppose from the random forest I came to some prediction, and from the predicted values I came to know that the predicted values and the actual values are differing too much. So that is there's, uh, variation present, and high bias as well low variation between the predicted values, but the bias between actual values as well predicted value, that is a error is too high. Error is too high, that is our random forest is a weak level. So what we can propose, or what we can do adjustment in our classifier or learner method, so that the learner method will be strong learner, strong machine learning learner method. That is a strong machine learning algorithm. So for that, boosting is a solution to handle the case, and we are going to see exactly how it reduces our error between the actual value as well the error between actual and predicted value. So after performing some n number of iteration, n can be anything, capital N is a number of iteration and it can be anything. So after performing that number of iterations, we come to the conclusion that whether error reduces or not. If it is not, then our learner is not performing well. So that we have to test, our train data and test data with different machine learning. So the method, if it is not giving the low error rate or if it is not giving the high accuracy, not essentially high accuracy, but considerable accuracy to predict the well, it should not be like overfit the model, but it has to be uh, maintain the trade-off between bias as well as variance. So one thing we already discussed as bagging, this is the second thing as a booster. So suppose we start with a model which is poorly fitting our data. So we iterate the same data, uh, having the n number of iterations, and iterating the same procedure multiple times will produces the minimum error rate. That is, it gives us the at the initial place it gives us the classification, but at the time of performing n number of classification or at the n number of iteration, that will gives us the uh, minimize residual error, but it gives us the uh, good classification accuracy. So exactly what algorithm says. Algorithm says that you have built the base model. Suppose it is a random forest. The basic machine learning model is a random forest model, and with that you have built fx. Fx is your function. Function means the machine learning model. It's a random forest for consideration, and your y will be like a response. So these are the actual training model response. Then at the second stage, what you have to do? First stage you already built with a base model, that is a random forest. That is your F1x. At the second stage, what you have to do is that H1x is equal to y minus F1x. So what are the predictions from the model, from the base model? We are considering those as F1x, and y minus F1x will be the residual errors that comes out from the base model. And at the third stage, what we are doing, we are considering the same model and we are fitting the machine learning model, or we are fitting the algorithm not to the actual responses but to the H1X, that is a residual from the part 2, that is a that is from the step 2. Suppose I have y equal to 1.1 as actual value, and this is a single training observation, and I fit model random forest to that particular observation. Then at the second stage, whatever the value predicted by the step 1 will consider as a predicted value, and will take out the difference between the predicted as well as actual value. We'll consider it as H1X, and in the third stage, what I will do is that I will repeat the same model again to the residual, and after performing the same thing, will come to the conclusion, and will come to the conclusion whether the error is reduced or not. So in the backend, it is a kind of black box. So actual algorithm, how it works. Suppose I have 10 number of observations. So my my small n will be 10. It's a number of observations in the training data set. Then after after fitting the random forest model, I come to the conclusion. I come to the predicted values of those 10 observations. Then I'll take out the difference of those 10 observations as well, between 10 observations and 10 predicted values. Then the it's a classification, so it can be either 1 or it can be either 0. The same is the case with the regression, so we'll consider that in that. So this is the case with the classification I'm explaining. So it's a 1-0 output has to be there. Suppose actual data with actual data and with predicted data, 5 observations among all 10 observations are correctly classified, but 5 observations are not correctly classified. So those 5 observations which are not correctly classified will have more weights, will have, I'm again repeating, will have more weights than the observations which are correctly classified. Suppose first 2 observations, alternatively 2 observations are correctly classified. Then alternatively 2 observations will have lesser weight than the observations which are incorrectly classified. Suppose I am considering 1 as a weight to the correctly classified observations and 2 as a weight to incorrectly classified observations. So my 1 become the weightage for the correct classification, and 2 become the weightage for incorrect classifications. And I will take the same weightage to perform the step 3. Now these are the generally using boosting algorithm. So GrBoost means a gradient boosting, XGBoost means the extreme gradient boosting, then AdaBoost, all of us may know it. I hope that. So it's adaptive boosting, and with adaptive boosting, we are also using the bagging sample. So what are the bagging and what are the bagging sample that we already discussed? So the same sampling procedure we are using in AdaBoost. And the fourth one is the stochastic gradient boosting. There are many more boosting algorithms also present in the literature, but these are 4 which are people generally papers and people generally use. Many travelers use extreme gradient boosting. Why they are using? Because it minimizes the error rate. That's why they all are using the extreme gradient boosting. And these all procedure are gradient descent. These all procedure are based on gradient descent method. Basically, gradient boosting is an optimization algorithm to reduce our error between the predicted value as well actual value. So it mostly it is referred as a optimization algorithm, and these four methods are generally people are using, and most of the industries are using this four base algorithm. So we'll explain actually what is boosting and how we are implementing it in R with a small data suite. The data suite is taken from the UCM machine learning repository, and the data set is about the credit card approval data. So there are uh, 15 features available in the data, and 690 observations are available. Among the 15 observations, we have one more observation. So in total, they become like 16, and the last one is the response, either the credit card is approved or not approved. That is the response, and all 15 are the parameters which says that we have to approve or we do not have to approve the credit card for the particular user or particular like account holder. That's then it's about the CC application data, and it is taken from the UCM machine learning. So I'm just showing you the code, and simultaneously we can run the same just opening R. Making the case study first. So we'll take you through the code as well as the observations, and let's see what are happening. So meanwhile we required some packages also. So packages I saved it in package frequently. That will be regular usage repository for me because I'm frequent using these packages. So I just have clubbed all them together, and it is processing. So the Rio is a library from R which is useful to import data as well to export data. Why Rio we are using? So actually in R there are different type of formats of the file we are importing as well. We want to export the file in different formats also. So Rio is a combination of all such types of library exist in R, like fread, data.table, then read.table, then scan, Excel sheet, so read.xlsx. Rio contains all those type of format, so we are using Rio, and Rio is a much more mature package to handle the different type of data set. And this is you can see here. So this is the data set, and the names of the columns are not provided, and data is a mixed type of data set. So it's a interesting kind of assignment or experiment we can have. Like see, some variables are in continuous format, and some variables are in character formats, and some variables are in target variable is in binary format. So I'm just renaming the last column as a response because it's a positive and negative. So positive means what happened, the applicants or the account holder is approved for credit card, and negative means the account holder is not approved for credit card. Now I'm just removing the anomalies present in the data. There is some observations are the missing information, and that is replaced by question mark in the data set itself. So I'm just replacing it with a zero. Then I'm recoding our data, that is the labels which are present in the data. So you can have it a structure, and see this character are having different levels. So all the labels will this loop will consider, accordingly the loop will recoding all the levels. So just running it, and you can have see. So after running this, you can see the variable has 3 levels, variable 2 has 350 levels, variable 3 is a continuous variable, variable 4, variable 5 has 4 levels, variable 6, variable 7 has 15 and 10 levels accordingly, respectively. Sorry. Variable 8 has variable 8 is a continuous variable, then variable 9 and 10 has continuous, not continuous. Variable 9 and 10 has 2 levels respectively. Then variable 11 is a kind of continuous, that is a integer type of variable. Variable 12, variable 13, and variable 14 has 2, 3, and 171 labels respectively. Variable 15 is again a type of continuous or integer variable, and last one is a response variable. Now, the response is present in plus as well in minus sign. So for fitting the algorithm, or for fitting the mold, we have to convert it into 1 or 0, so 1 and 0. So it can be either in plus and minus, or it can be either 1 and 0. So it's a better to have it in 1 and 0. So I'm just replacing it with this code, and it has to be factor. So I'm just doing it as a factor variable. Now I have to what I wanted to build a machine learning model on training data set, and validate it on the test data set. So 60% is my training data set, and 40% is my testing data set. So whatever models we have fit, we have fitted, whether it is right or wrong, whether it is underfitting, whether it is overfitting, that that we should come to the conclusion. And for that, we have divided our data into training as well as testing data set, and 60% is a training data set, 40% is a testing data set. So that's why this zero point 0.6 is coming. So zero point 0.6 means the total dimensional of the data, the number of rows, that is 690 into 0.6. That will be our training size, and remaining is our testing. So, so So shuffle, what shuffle does is that shuffle is the command from the permit package, and what it does that it shuffles all our observations, and it gives us the randomly selected observations with the row and number, whatever the row numbers actual data set have. It will use the observation to that row number. So I'm just shuffling to produce the randomness in the data set. That's why. So I have to include the package permit for that. So just a moment. Permit. So library permit. So training and remaining is a testing data set. You can have a bit of test data set. You see, it is a recoded in specific reports after running that loop which we have seen. Then I am using the uh, like decision tree model, and so mm, a response is like represented by response, then predictors, and it's a formula. Okay, so we are not using these things which we have used in banking, and the three steps are mm, the three steps are showing not exactly, but these three steps are helpful in building a formula so that we don't need to type each and every variable name. Suppose here only we have 16 variables, but if we have like 1,000 variables, then we don't need to type thousand variables, so that the three lines will be helpful. Now we are fitting this R part model. So for that, what we need to do, we have to import the library R part. So this is the R part library, and we are fitting this model. I'm just clearing this model. So this is the R part, and we can see the rules formed in fit. Fit is a first base model which fitted on for 14 observations, which are the 60% of 690 complete observations. Then we are trying to predict the same without a response. We are giving the new data, and with the help of actual fit, we are predicting it. So it's like the R part is giving the probability of the observation classifying into zero, and the probability of the observations or the instance classifying into the one. Whichever is higher, we are considering that is a final class of the particular observations. Suppose observation number one has zero's probability is 0.6, and observation number one has a zero which observation number one has a one's probability is 0.4. Then we are considering the class for the observations is to be maximum between 0.6 and 0.4. So that has to be like 0.6. Then maximum of 0.6 and 0.4 is to be 0.6. So the class of the variable 1 is to be 0, because the probability of the probability of the observations in getting the class 1 is higher than the probability of the getting a probability of the observations getting into the class 1, which is a 0.4. 0.6 is greater than 0.4. That's why we are considering the class for the first observations is 0 the class. Similarly, all observations we will have, and the same we are running. If the prediction 1 is greater than prediction 2, that is a if the probability of the class 0 is higher than the probability of class 1, then assign the 0th class right assign first class, the class 1. That's what we are doing, and we are getting this thing. So it is present, and here are the brief we can have, short brief we can have, like the classes predicted at 0 are 2, 0, 1 instances, and 2 and 3 instances are produced as a 1 with our training as well as testing data set. Now we are again repeating it. So the same one you can use with the carrot package also, because our part is also available in the carrot package, and which is named as a train data, and here you can use like as I have shown our part, this thing you can use in the carrot, and with carrot also you can perform the same thing. So I'm just excluding this part because it is the same thing, and the tagging also. So now we are going to boosting mode. So it's a head of what the base model we have trained. Now boosting model. A boosting model is that the observations which are not correctly classified will have more weight. That is the basic assumption of the boosting. So we are just taking the observations which are not uh, correctly classified. So B, C. So false are 402 and 2 are like 12 observations. Now new weights will assign if this is the true, that is the 12 observations are not correctly classified. So we will assign weight as 2 to these 12 observations from the training data set, and the same we have written in the line new weight equal to if else more weight equal to true. If more weight equal to true, then it has to be assigned weight 2, whereas it has to be assigned weight 1. Now this is our first boosting state, and I think nomenclature is not there. So we'll just predict it, and with the boosted tree we have predicted these observations, and we are again performing the same thing. If it is the probability of 0 is much more than probability of predicting the class 1, then it has to be classify the observations in 0 as a 0 and 1 according to that, as we already discussed. So it's a prediction. So yeah, it's a correct. So it's a prediction of the boosted tree from the mm, from the base uh, model, and we can have the head of this. So these are the random samples like 169, 86, 331, 60, 205, 336. These are the six top observations in six top instances we have, and this is a boosted accuracy where you can see the difference is before it was like a zero class has classified 20k observations, where it has been changed. Now it is going down to 194. Now we will compare the result between the original base model and the boosted tree model. So this is a classification table of original model, where we have classified exactly 193 observations which are from the class 0, that is the instances or the account holder which are not qualifying for the credit card are 193, and we are correctly classified it as a 193. But in totality, we missed 8 such instances that are not correctly classified. This then the observations which are not eligible for credit card, but from our original base model, they come into the bucket. They come into the bucket that they are eligible for getting credit card are 4 in number, and 209 observations like they are eligible for credit card, and uh, the model is showing that they are eligible for credit card. These are 209. Now we are seeing the performance of boosted uh, tree, where we can find out the number of observations which are correctly classified with tag that the instances which are or the account holder which are not eligible for credit card or the credit card has not been approved for the users are 190 number and which is lesser than 193 predicted by our base algorithm. And the number of instances the number of instances which are correctly classified with a tag that the instances are able to get the uh, instances which are approved with a credit card approval 213 which is more than 209 with the base classifier. So boosted card or the boosted decision tree has increased our performance, which we can see from this region. So the error from the base tree was like 0.028. The error from the boosted tree, sorry, so it's a 0.026, which is lesser than the original base model. Then accuracy of the original model is 0.97 and accuracy of the boosted model is the accuracy of the boosted model is a 0.97343, which is higher than the 0.9710. And this is a comment that boosted card has a low error rate and high classification accuracy compared to the original card. That is, whatever we have done, so whatever boosted model we have fitted, so we have hit, so that gives us the more accuracy, more classification accuracy and low error rate as compared to the base original model. So this is just a summarizing table you can have. Just a minute, just a moment. For Keval, I just need to um, run the package neat that gives me the like table structure format, and here is the brief summary. You can see from this. So original model, for original model, it's a error is a 0.028, and for boosted model, the error is a 0.026, and accuracy for original model is a 0.9710, and accuracy for boosted model is a 0.9734. So you can see the difference between the predictions with just a 690 observations is drastically changes if we are putting boosted model. If we are altering the weightage assigned to misclassified observations, then we can have the improvement in our classification, and that's what the boosted tree algorithm suggests it. Now we can iterate it to the n number of the observations or n number of iterations, and we can have like a desired result or the good classification accuracy. I can't say it's a desired result, but it's a good classification accuracy. You can have this code, you can refer this thing. So it is there in the code itself, in the presentation itself. So I'm just proceeding to the next slide. It's a comparison of results. We can see this prediction accuracy has been increased in boosted trees as compared to the base classification trees, and we can iterate it to the n number of iterations to get a desired accuracy, or to get the less number of false positives. Now, when to use a bagging, why to use bagging, and what are the reasons to perform it. between bagging and boosting. So the table summarizes for us what is the bagging, what is the boosting, as well what are the what are the circumstances to perform the bagging as well as boosting, bagging as well as boosting, and uh, the combination of body how we can perform that. The same is also suggesting to this table. So in bagging, we are subsetting the random sample. So the complete sample consideration will be like a properly random sample. In boosting, it is a preferential sampling. So exactly what I mean. Suppose in the base classifier, I have misclassified some observations. So I will assign the weights to misclassified observations more than the correctly classified observations. That's why it's a preferential sampling. Then reason to perform, why we are performing banding to minimize the variance, and why we are performing the boosting is to increasing the predictive power. Now, backing can be used in a random subspace that we can have like a random sample. That's why it can be performed in random subspace. But boosting, we are using or we are assigning the more weights to only unclassified, only not correctly classified observations. So we are not commenting on that. And in bagging, we saw that we are either taking the best sample among the capital N samples which we have, or we can have the weighted average of all the capital N samples. Where in boosting we are measuring the we are voting the majority. So the sample which have the which have more correctly classified observations, we will consider that. Now, I'm just proceeding to the simple gradient boosting. And what is exactly gradient boosting? So boosting, we already saw what is the boosting. Now, what is a gradient? Gradient is a step-by-step uh, performing observations or step-by-step of the column-wise as well row-wise consideration of observations, and we are optimizing our machine learning model as well machine learning algorithm with this boosting and gradient boosting. Actually, we have reduced the error from boosting itself. Now we are increasing the predictive capability, or it's a kind of optimization algorithm, which is the extreme gradient boosting. But we are just considering simple gradient boosting in this presentation. And now later on, we will see what is the extreme gradient boosting or stochastic gradient boosting. The same data which we have considered is from Google only. So the data set is age data set, and it is predicting. It is a regression tree. There is a classification regression tree, and it is producing the age of the individual based on the certain parameters. Uh, so we'll just take you through that. Now, before proceeding to the case study, what exactly boosting gradient boosting algorithm does? Now we saw that bagging reduces the variability, boosting reduces the biasness. Then what gradient boosting do? What gradient boosting does? So why it is necessary to have the gradient boosting algorithm or to perform the gradient boosting algorithm? What happens after performing boosting algorithm? We have some residual remaining. The task of reducing the necessary residual errors is done by the gradient methodology, and the methodology is the same one as this gradient boosting. We are performing boosting, but with a gradient stepwise algorithm. What does it mean? So we are going through column wise as well. We are going through the row wise, and we are finding the optimal path or optimal sample or optimal way through which we can select the best sample, or we can reduce the residual error between the predicted and actual. So this is how the XGBoost works. So in the XGBoost algorithm, what a step-by-step procedure of XGBoost algorithm is, we are fitting the boosting model, then we are predicting the residuals in the second step. In the third step, what we are doing is we are refitting the model not to the response and to the residual from the stage 1. So I'm just explaining this step again. We are refitting this model to the residual which we have got from the step 1 and not to the actual responses. So that is the difference between actual boosting and gradient boosting. So it comes to know whether we are able to actually reduce the residual error or not. So in boosting, we are at certain level we are reaching, but not beyond that we are reaching. So for that we have to go by gradient descent algorithm, and in the black box of gradient boosting, there is a gradient descent algorithm. So we'll just take you through this gradient boosting algorithm, and I think I don't need to take it to R because it's a simple R code, and you can have this uh, your R session. So this is the XGBoost data, and we use the same thing. It's a data, and we use the same thing. Linear regression model. Wait, I'll just so this is the data for simple gradient boosting, and it's like this. So it is having age, which is our predictor. It is not predicted. It is a response, and likes gardening, plays video games, and likes hats. These are our predictors actually. So these are explanatory variables, and the dimension is 9 by 5. So structure is like fun or logical or character, and remember, like person ID is not we cannot consider it as a variable because it's the same thing as serial number. So we just have 4 variables, and then one is the response and others are predictors. So which are true, so we'll just replace it by 1, and other are replaced by 0. So automatically we can this small command, then dimension is 9 by 5. This is what structure of the data. Now we are putting this model. So it is not a card model, but it is a linear regression model, and we are putting it. So it's just printing. So these are the coefficients of each variable. This is the intercept, this is the like gardening coefficient, then this is like video games coefficient, and like hats coefficients. Now we are predicting it with the predict command, and the prediction we are predicting all 9 observations. So all 9 observations are predicted. Now new matrix is provided, and new matrix considered original age then predicted age and the residual, that is the difference between actual age and predicted age. Now we are binding the data in the new format, and here age, like gardening, plays video game, like hats and residuals are together, and we are fitting the model to the residual error, and this is the model. Okay. So it has to be data frame before passing it to the lm command, and lm is a short form for linear model. So the intercept are like this, and you can see the intercept has been decreased. Now we are predicting it new values. Then this is the difference between the uh, actually this is not difference, but this is the combined prediction variable, where combined prediction variable is the sum of the previous prediction as well new predictions, whatever the new predictions which we have did. Addition of both the variables is a combined prediction, and we will have like final residual as a newly predicted values minus uh, actually can be like absolute difference of the uh, original value and combined prediction. So these are the final residuals. Just a minute, run this thing. We have this new matrix, which is the combination, or which contains the columns like original age, then predicted values and the first predictive and the first model at the time of first fitting model, then the residuals, then predictions at the second stage, then the combined predictions, and after having the combined predictions, so combined predictions will be like 13 minus prediction 2, that is 13 plus prediction 2, so it suddenly becomes 13 minus 11.7. So 14, 15. So this is a combined prediction. So prediction 1 and prediction 2. Prediction 1, the same thing is prediction with the prediction 2. 8 plus 0.2, 14. Then prediction 1, 1.2. So it will become like 15. Then 46.5, and this minus 21.5, then 24.7 and 10.3, 16.7 and minus 11.7. So similarly, we are doing for all the observations, and the final residuals which we are getting is this one, which is much lower than what are the residuals which we are getting here. And at the end, we are combining this model, and we are done with the gradient boost. Now you can refer this code, and you can ask if you have any doubt after referring this code. So I'm just proceeding to further slide. So I hope you got the idea of what is a tagging, what is a boosting, what is a simple gradient boosting, and what is a gradient boosting. So the implementation of R is completely done, and the packages which we can use in R, like it's adaptive bagging, ensemble model, and carrot, boost, and boost, XGBoost. These are the packages available in our And in Python, we have bagging, boosting, and XGB. For all these three tasks, we have like a scikit-learn, boost for Python. These are two modules we have available in Python, and in the next session we'll see the implementation of bagging, boosting, and gradient boosting method in Python. So we already covered the theoretical background and implementation of bagging boosting in XGBoost, not XGBoost, but simple gradient boosting in R. So in the next session we'll learn. Uh, we'll go to we'll go through the case study from Python covering bagging boosting and gradient boosting, where we'll also consider simple as well extreme gradient. So that's end of this presentation, and thank you.